Hey everyone, welcome to my presentation with the multi-scale computational visualization and modeling of optical nanomaterial and application. So optical nanomaterial is one of the interesting material because this material has a features less than a wavelength of light. So typical is less than like 780 nanometer, for example. Because of this material, they have a strong interaction with the lights and capable to produce a beautiful color iridescence or the structural color that we can see in the nature as well as the mimics the artificial material. And some of this material has a semi-transparent properties that we see, like for example the thin films. So one of the example is morpho butterfly wings. So the colors that we see on the wings actually is raised from the nanostructures. So it's a dielectric nanostructure that produce a blue color iridescent. So as far as we can find some of the example in the ancient artifacts, for example, the Languscus cups. So the structural colors, actually this color actually is arised from the metallic nanoparticle itself. So it depends on the light shining on the objects. So they can produce the ruby reds or the jet green, like this one. And the study of the optical nanomaterial is a multi-step process. So they always start with the iterative simulation at the nanoscale and then go for the lab fabrication at the centimeter scale. So once they're done, so they do for the optical categorization. And this process is going on and on again because this is to optimize the structure. So it's a time-consuming process as well as the resource-intensive process. So our question in our thesis in our mind is it possible to predict the nanofabricated material looks and behave under the real-world environments as well as human scale? So the purpose of this thesis, we want to utilize the computational methods. They use a wave and the particle simulation at a different size scale to generate the visual appearance of the nanomaterial. So the electrodynamic simulation is one of the examples that simulate lights as a wave. So to simulate, to predict, understand the light interaction at the nanoscale. And so the finite difference time domain is one of the key, the methods that used to solve the Maxwell equation over the discrete spatial grids and yield the radiometric quantity like the time average electric density and the spectral distribution. But only this delimitation of the FTT is because it's a small simulations is allowed in a single computer, because large simulation they require lots of memory as well as the storage space. So for another side of the light simulation, we have the light simulation as a particle, the physical-based rendering methods. So this is common in the computer graphics. So they simulate the visual appearance by tracking the light ray propagation in the virtual environments, and this gives a lot of benefits because it can produce a high degree of photorealism image at no time. And the image they produce is a physical base, it's a physical correct because they use a geometry optics. So to make it happen, they use the rendering equations that models the light transport by sending the handful of the ray out to the pixel and trace the light path between the surface until they reach to the light source. So the technique they use is a path tracing. And because this is a geometry optics based rendering light simulation approach, so the PBR failed to describe the wave interaction at the sub-wavelength scale. So they require additional analytical and as well as approximate models to describe those surfaces with the nanomaterial. And so because of that, by considering both efficiency and the advantage of the PBR and the electrodynamic simulation, so we propose a multi-scale methods that utilize these benefits to simulate the visual appearance of the nanomaterial. So under the real-world environments, for example, the thin films as well as the plasmonic nanostructure itself. And then lastly, we apply this into the daylighting and glare control. So this is the first ever result that we're capable to produce a computer visualization of semi-transparent metallic thin films, because the thin film is structurally simple and yet the visual appearance they have highly effective at the sub-wavelength scale. So our multi-scale methods has a two scale of the roughness over here, and we treat them independently. So for the nanoscale, we assume that the nanoscale roughness is come from the surface imperfection of the substrate. So where the nanoscale roughness is a surface imperfection due to from the metallic films. So at first, the first step we start with the wave simulation, the FTTD simulation that we simulate. We simulate the light interaction with the rough thin films. So on the surface, and the roughness is generated from the surface coloration functions. So once we have that, so we extract all the RGB reflectance, and so later that we can apply it to the physical based rendering material. So for the nanoscale roughness, so we use a microfacet theory, and this is the typical way that they use it in the computer graphics to describe the effects of the microscale roughness. So there's two important terms in the microfacet theory. This is the first is the normal distribution functions. So it's a function that describes the normal distribution functions. And then so we have the second one, the masking and the shadowing functions that combine together that we can produce a PBR material to render the visual effects of the thin films under the real world environments. So for the Fresnel reflectance, so we do a modification. We use a slick approximation instead of fully calculate from the FTTD simulation, because they require tremendous amount of the time and computing resources. And the slick approximation is a very simple and accurate computational efficient to describe the visual appearance of the bulk material like metal, glass, and various plastic. So all we need, we just need the Fresnel reflectance at a normal incidence. Because this is the first time we apply the thin films with the slick approximation, so we perform some analysis calculation. So this is what we have here. So the slick approximations with the Fresnel reflectance is calculated from the TMM, the transfer metric methods. So the error is showing in the percentage from 0 to 50%. So all we can see here, so majority of the error between this approximation and the Fresnel reflectance are very low, except for those at the shorter wavelength at a high incident angle. So we believe this is a best approach that we can use it to approximate to render the visual appearance of the thin films. So in order to create the real world lighting to render the appearance, so we need the real world lightings. So what we did here, so we have two lighting setup here. So we have the interior lighting rooms and the studio lighting room. So the interior lighting rooms, actually is a 360 image capture. The capture 360 image, and then so for the studio room is a 3-point adjusted box lighting. So with the freedom that we can adjust for the color temperature as well as the intensity. So both of them have the similar setup, so which is the thin films placed on top of the printed paper with the UBC logo. And this is the first ever image that we render, and we compare with the real fabricated sample from the lab. So what we can see over here, so we have the colors, the gray bluish colors on the renders. So we show almost the same like the right side, as well as has the similar reflection highlights, the mirrors that cast on the films. So, but we have a little bit wavy reflection highlights on the real fabricated films because of the pressure that we apply to hold the thin films. So because of the PBRs, this allows us to do some degree of freedom to play around with the lighting setup. For this case, we adjust for the color temperature from the warm lighting to the cold lighting environment. So what we can see over here is we see the transition from the warm, like the brownish color, gray brownish color of the films, turn it to the gray bluish color because of the color temperature change. And this allows us to do for more freedoms to adjust, and this allows us to study about the nanoscale roughness of the films. So what we can see over here, so this is the collection of the AG films with the various of the thickness and the roughness scale. So what we can see here, so the transition of the color change with the increment of the roughness scale from a gray bluish to gray brownish, and then from the transparencies are reduced due to the thickness increase. And then so next, so this also allows us to study the multi-layers effects with AG TiO2. So the TiO2 here is start from 18, that we increase the thickness up to 57. So we see over here, so we see the change of the transparency on the roughness scale when they increase, and then the color change from the gray bluish colors to the brownish colors. Since this is a multi-scale roughness, so this allows us to combine the both nanoscale and the micro scale roughness to see how this the different appearance can be looks like. So on the different substrate. For example, we have 4 types of substrate here. So we have anti-glare, ground, frosted, and edge glass. So what we can see over here is, so there's a clear patterns that the reflection highlight is disappearing with the increment of the nanoscale roughness. So let you see further, so we render the same setup. So with the on the chest pieces. So the further end from the camera is the AG 25 nanometers, and then the pieces that close to the camera is the AGTRO2. So what we can see on the circle here, so we have the reflection highlight is disappearing. So from the specular reflection highlights to matte, and then it's like the diffuse finish. So the takeaway from this approach is we show the feasibility of to render the physical appearance by combining the FTTD and the PBR methods, as well as we can create a PBR material methods based on the FTTD simulation and the slick approximation and microfracture theory to describe multi-scale of the effects. So next, we move on to the more interesting structure over here. It's a plasmonic metallic nanostructure. As we know, because the plasmonic response is generally dependent on the angle and the polarization, as well as the configuration of the nanostructure. So for this case, so we choose 3 structure over here. We have the nano hole array, nano disk array, and the hybrid structure, the hole and the disk array. So the simulation method is slightly different than what we did on the before, because we have to consider about the angular dependency. So that's why we run the multiple FTTD simulation from the normal incidence. And then so once we have that, so we capture all this and we perform the near field to far field transformation so that we can extract the plasmonic BSDF file that create the PBR material for the render. So to give you a little bit more context about what is a plasmonic BSDF models, so the plasmonic BSDF model actually is follow the definition of the BSDF file. It's a ratio of the spectral radiance to the spectral irradiance. So what we did here, so we just take the near field transformation of the reflected or the transmitted of the E field over or the far field transform of the E field that received from the substrate. So to decode what is the BSDF looks like, so this is the BSDF that is a numerical data they combine, they record in the data file. So this is what we see over here. So they tell them the render engine about the scattering distribution. And so what we see on the right side of the images, so that is a scattering distribution that we produce in the image. So that's going to tell us about the color appearance of the object based on the camera viewing angle. So similarly, to create a real-world lighting setup, because we want to preview the structural colors from our multi-scale. So we have 2 sets of the lighting setup here. So with the interior rooms and the studio room. So we have the similar lighting setup that we used at the before, but only the different we use a spherical substrate and the petacar. So the petacar and is coated by later is going the body of petacar is going to coated by the nanomaterial, the nano array. So this is the first ever result that we have here. So it's a silver nano hole array. So what we can see here, so there's the color gamut is changed from purple to jet green on the reflected colors, and then so we can see some angular selective properties because of the colors different spot from the front facing and also the way from the camera. And if we notice that there's slightly dark at the bottom of the sphere because of the room that we capture has the darker carpet, so that carpet reflect to the sphere. So because of this, so this allows us to study more detail about the effects of the metal type on the plasmonic color generation, and this is what we have here. So for the AG and the aluminiums, so the aluminum's colors is retained almost the same, even the periodicity diameter is increased, because we know Aluminum has a higher ohmic loss at a visible frequency than silver. So that's why they cannot support for the SPP, the surface plasmon propagation like silver before. So next we move on to more interesting colors like stronger wider color gaming structure, the silver nanodisk array. So what we can see here, so we have the strong colors even with the small change of the diameter and the periodicity, because this is attributed to the metal insulator metal sandwich structure. So which produce the stronger plasmonic resonant coupling interaction. So that result a peak at the transmittance and the deep valley at the transmittance spectra. So that attribute to the colors that we see over here. So lastly, we have the high peak structure of the aluminum nanodisk array. So we vary the separation distance. So what we can see over here is, so there is a color start to fading from blue to khaki colors, because they still have the angular dependency, but when we increase the separation distance, so they're going to reduce the plasmon hybridization between the hole and the disk. So the result of the colors fade away. But however, we can recover this by changing the diameters size from 50 to 110. So what we can see over here, so the colors start to recover back to blue colors that we see over here, because the increment of the diameter is going to increase the nearest coupling effects between the hole and the disk array, because they are getting closer, and that's recover for the resonant interaction that need to produce the blue colors. So next, we want to study about the color generations due to the nanoscale roughness. Because we know the fabricated sample is not perfectly smooth always, so they still have some level of surface irregularity at the nanoscale. To study the effect of this in the color generation, so we use a silver nanohole array for example for the study case. So for the surface roughness, so we use the similar surface coloration functions that we use in the thin films, but with the various in-plane and out-of-plane roughness scale. And the approach is almost the same like what we did for the plasmonic structural colors, but only the difference that we introduce the surface roughness on the whole array. So this is the result that we captured so far, and so we have two set of the roughness scale. So we have the in-plane and out-of-plane roughness. So what we can see here, so there's a slight color difference in the in-plane, but for out-of-plane roughness, when the roughness scale is increased, so we see the purple colors start to fading away or become less saturated, and the delta E, the color difference, become more obvious due to the out-of-plane. So what the summary that can brought up from this one, so the out-of-plane roughness has a great effects on the color generation compared to the in-plane. So as the out-of-plane roughness can be drastically changed, the plasmon interaction, the resonant interaction at the nanodisk array, nanohole array. Sorry. So lastly, we apply this multiscale in the daylight and the glare control by the nanomaterial for the multiscale models, because we know like the excesses of daylight in the work environments can cause an issue for those like working near the windows. So they're going to cause the glare as well as the potential of the heating. And we know the thin films is one of the exciting technology that apply it to the common technology that apply it to the window glass. So they're capable to alter, to change, to allow the lights to enter to the space. So the addition of the light thin films applied to the window glass can turn the highly transparent glass to be angular selective and the spectral selective layers to enter to the space to regulate the amount of the daylight to enter the space. So our question is it possible to use our method to study like the thin films in general? So that's why we have three window structure of interest here. So we have the window plane, which is a window glass that coated by the thin films, and then we have two daylight redirecting structure over here. So our approach is almost similar like what we did like before. First of all, we perform the FTTD simulation to extract the RGB reflectance and the transmittance so that we can create the radiance PBR material. So once we have that, so we can run the climax-based simulations, and then so to evaluate the daylight performance based on the metric that we see here, the two categories over here. So the daylight performance metrics, we have the spatial daylight autonomy, and the annual sun exposure, and the average illuminance, and the relative average illuminance, as well as distribution. So for the glare performance, we choose specific for the glare daylight glare probability, the GGP. So because this is a climate-based simulation, so we need the 3D models. So the 3D model, the interior of the space, we models as we have a model as a like south-facing. South-face has the interior model of the room has a south-facing windows. So the location that we set over here is a UBC Okanagan's, and then because of UBC Okanagan, because it's climate-based, so we choose the Summerland as our climate study. For this case, a PB. So the climate-based study. So we have two set of the glare, the daylight sensor and the glare sensor, so that we can use that to calculate to generate the daylight metrics, daylight performance metric, and the glare performance metric for the calculation. So for the glare assessment, so we choose specific on that occupant's viewpoint and orientation, so which is facing the window. So while they're sitting on the table, sitting on the chair, in the sitting position. So next, so this is the first ever result that we apply our FTTD simulation result, the reflectant and transmittant, to the climate-based simulation. So what we can see over here, so this is a drastically reduction of the daylight performance metric for all the variables with the AG films. So particularly at the thicker layers of AG, it's because this is attributed to the higher reflectance of the AG films. So that results in reduction of the average distribution, of the illuminance, as well as the distribution lux in the indoor space. So, however, for multi-layers, so the reduction is not so obvious, not so obvious like the AG single layers films, but they still have some degree of the reduction. So to study further, so we perform the day-specific daylight simulation to understand how the different sun angle can affects on the performance from the highest sun angle in the summer to the lowest in the winter. So what we can see over here, so we have the bluish color in the render in the indoor space for the AG films, and we have the greenish colors rendered in the indoor space. Because the bluish colors in the indoor space for AG films is more severe, so that can cause some problem in the color rendering index when working in that environment. So next, we study the light converts to see how this can improve the glare experience. So what we can see over here, so this is the annual glare chart, so that showcase the hourly DGB over the time of the year, from January to December for each day. So we can see the addition of the layers of the films that reduce the glare experience. But to study further, so we pick a day specific at March 12 noon. So what we can see over here is, so with the addition of films that reduce the glare experience, but for AG50, so we see that there's a dark blue in the false colors. So that's going to indicate, so that's going to cause more they're going to cause like darker room in the indoor space working in that room. So lastly, because we skip for the flat slat, because that flat slat doesn't have any improvement on the daylight redirecting, but for wing flat slat, so what we can see over here, so the increment of the average illuminance at the ceiling, so that indicates that partial of the lights of the daylight, so it's redirect upward to the ceiling, so that increase the ceiling of the illuminance at the ceiling. So that's going to tell us about some improvement on the daylight performance and the glare performance. So to study further, so we perform the day-specific structure for different sun angle. So what we can see here, so by comparing with the bare windows, so we saw the blight spot on the floor is disappearing, because a portion of the light is redirecting outward to the ceiling. So next, we want to investigate the performance, how this structure can be improved, the glare performance. So what we can see the wing flat slag is, so the wing flat slag can reduce the glare occurrence in the indoor space, make it more comfortable, but they cannot reduce the glare at the afternoon because that's the brightest of the day. So next, we want to see how this the glare performance at the afternoon, because to see how this structure can be helped that improve. So this is what we see over the occupant's position, and so we still can see there's a bright spot on the windows, and then so they still have the low intensity fall on the table and the floor, but that is not the typical like serious. And also we saw some improvement on the bright spot on the ceiling, so that's going to tell us that there is some degree of the daylight redirecting effect that we see over here. So finally, in conclusion, so with our multi-scale method, so we are able to render the visual appearance of the thin films under the multi-scale influence of the roughness, as well as at the different lighting condition and the substrate. And also we're using extend this idea for the plasmonic structural colors, that we can render the color appearance, the structural colors for different structure, as well as the nanoscale roughness. And lastly, we apply our methods for the daylight and glare control for the 3 different window structures. So what is the next step to moving forwards? So we can suggest that to move on to push the research to the next level is to use more high efficient computational efficient methods, because we know FDDs take a lot of time to simulate, as well as using higher accuracy of the FDD algorithm, and also using some of the rendering engine like the spectral rendering for better quality. And also because of this method allow us to study the more complex structure. So over the past, so our works have been published in some of the top conferences in the computer graphics, and we received multiple awards from the conference, particular in the SIGGRAPH. So we have we have 4 papers are on the way to submit. So lastly, so because of this method, the PBR method, so that allow us to have the new way to study about the effects of the structural colors by render the virtual experience to see how this color change in the virtual space. And so what you see here, this is a virtual space that we created for the SIGGRAPH conference. So they can just jump into the space and look around. So feel free to pause the videos and then use a phone to scan the QR code to experience this. And this is also another one that we created a year before. So lastly, I would like to share the journey of my PhD in the startup world, because I was lucky enough that I can use and learn and use my knowledge to found a company and start to grow to today, the Mantis XR. And so we work for multiple commercial projects in different areas, from architecture, winery, to both manufacturer and some of the virtual experience company. So lastly, I would like to say thank you for everyone to stick around. Thank you so much.